You might think this nylon thread is just a piece of fishing line, but once you power it up, it can do something wild. It contracts like a real muscle, and then it can stretch back on its own. Even crazier, it doesn't need motors or complicated controllers. Instead, the action logic is pre-programmed directly into the fiber itself, like writing code inside a single thread. It can do not just contraction and stretching, but even more complex three-stage multimodal movements. In today's video, in just 5 minutes, we'll break down chromosome-inspired programmable hierarchical helical artificial muscles. First, let us look at its structural design. To solve the century-long problem that artificial muscles cannot simultaneously achieve large stroke and high load, the research team adopted 3 key structural strategies. The first is the chromosome inspiration. Ordinary single helix structures are prone to loosening and losing strength. By mimicking the highly folded structure of biological chromosomes, the team developed a second-order helical structure. This is like winding an already coiled spring into a larger spring. Moreover, the team established a complete mechanical theoretical model to verify this structure. The theoretical analysis is highly consistent with the experimental results. The second-order structure can effectively disperse internal stress, and it significantly reduces the equivalent force on the fiber cross-section. This explains, from mathematical and physical perspectives, why it remains stable under large loads without coil collapse. The second key strategy is an ultra-large initial pitch. Many traditional designs pursue force by winding coils very tightly, but tight coils cause the fibers to squeeze together and become unable to contract. This study forcibly pulls apart the coils through annealing and pre-stretching processes. This is like reserving a huge compression space for a spring. The data are very direct. Its contraction stroke reaches up to 88.1%, meaning a 1-meter-long muscle can shrink to only 12 centimeters. In extension mode, the stroke reaches an astonishing 860.7%. Under the same material and size, this second-order muscle has 9 times the load capacity of an ordinary first-order muscle at 50% contraction. It truly achieves both strong force and long travel. The third key strategy is the programmed manufacturing process. The team developed a regional twisting technique. By controlling rotation and constraint at different positions along the thread, they can make any segment of a continuous fiber self-coil to form a helix. Effectively, they are writing functional code into the material during manufacturing. This enables segmented customization without post-assembly. After looking at the hardware, let us now examine its control logic. The reason this research can be called programmable lies in its decoding of chirality. As mentioned earlier, this thread can be manufactured in segments. Here's the key point. If the self-twisting direction of the thread is the same as the coiling direction, this is called homochirality. It contracts when heated. But if the directions are opposite, this is called heterochirality, and it surprisingly extends when heated. Using this principle, the team made the upper section of one artificial muscle homochiral and the lower section heterochiral. After electrification, the upper section contracts and pulls like a biceps, while the lower section extends and relaxes like a triceps. With only one muscle, it drives elbow joint flexion and reset, with a response speed reaching 23 degrees per second. But does it end there? No. The team further developed third-order helical artificial muscles and explored a more complex programming space. The third-order structure has 3 layers of helices, and each layer can be wound in a positive direction, which we'll call P, or a negative direction, N. It's kind of like playing with combinations. Twist the layers in different ways, and you get different chiral patterns: PPP, PPN, PNP, PNN. This is like upgrading from a simple switch to complex logic gates. Different combinations can produce completely different motion modes. For example, some combinations can not only contract, but also be accompanied by strong radial changes. This greatly enriches the motion repertoire of artificial muscles. Beyond basic contraction and extension, This programmable muscle can also achieve complex biomimetic operations through clever combinations. The research team built an earthworm-like crawling robot. This earthworm robot was placed inside a thin glass tube. By utilizing differences in chirality, it can wriggle forward like an earthworm, making it especially suitable for operating in narrow pipelines. In addition, the team also developed a flexible finger. They programmed together a first-order helix with fast response, and a second-order helix with slower response but greater force. The fingertip uses the first-order structure, allowing it to bend quickly and wrap around objects. The finger base uses the second-order structure, providing strong gripping force. Experiments show that this hybrid design achieves a larger grasping enclosure angle than a single structure, with significantly improved grasping success rate and adaptability. This is just like a human finger, sensitive at the fingertip and powerful at the base, perfectly replicating the biological logic of grasping. In summary, the unique hierarchical helical structure, combined with optimization through mechanical models, perfectly resolves the contradiction between strong force and long travel, achieving a 9-fold increase in load capacity. Regional programming and chirality control, especially the discovery of 4 chiral combinations in third-order structures, endow a single fiber with multimodal motion capability. And this approach of directly writing control code into the physical properties of materials enables soft robots to stably perform complex anthropomorphic operations under extremely simple actuation.
If you enjoyed this, don't forget to like and subscribe so you won't miss more amazing robotics.